Okay, let's work a new topic. New topic is gonna be partial derivatives, and this is the continuation of your past lessons. You already worked with planes, with x and y, um, vectors, points in a three-dimensional space, the arc length in two-dimensional and three-dimensional spaces. So our next topic is going to be partial derivatives. And a brief explanation of this is if we recap or recall this old single variable calculation that we have done in this past, if we have an example like y equals to x, and let's say that x is equal to 1, so y is equal to 2. When x is equal to 2, y is equal to 4, x is equal to 3, then y is equal to 6, and so far so on. So you are used to have this as a dependent and this as independent. You plot this, you have only a couple of values. You have here x equals 1, x equals 2, x equals 3, x equals 4. You have this y here, y equals 2, then y equals 4, it's going to be 3, 4, and then you draw a line to connect all those points. And this is a typical two-dimension space with this um, single variable, one dependent and one independent. Now, if we want to move to partial derivatives, then we need to start looking at the multivariable relations. In this picture that I'm showing you, this is called level curves. Level curves or curvas de nivel. And this is very nice example to represent what the partial derivatives is about, because you have here, we can say, let me change the color here to black. Okay. We can say that this is the y-axis. Let me change the layer. Okay, got it. So this is the y-axis, and let's say that this is the x-axis. So the y-axis is from here to here, and y-axis is from here to here. So if for any combination, if you have here some scale, let's write a scale like this is 1, 2, 3, 4, 5, 6, 7. And let's write another scale here. 1, 2, 3, 4, 5, 6, 7. Now you have one value for y and one value for x. And these values that you have here, for example, if you choose y equals 5 and x equals 6, we draw here an imaginary line that represents the 5, and here some line that represents the 6. You will end up with this little point there. And in this particular case, the height of this mountain is going to be equal to something between 0 and 20 meters, maybe 10 meters. So let's say in this case that um, let's name that height equal to z. Yes, it's a function of x comma y. So if x equals 6 and y equals 5, then z is going to be equal to some value between 20 and 10 meters of height. So in this case, we have this height variable as the dependent variable, and this couple of variables here in this plane is going to show us, according to the coordinates, what's the value for the height is going to be. So you're trying to find the top of this mountain, you may find to see that maybe for x equals 4 or 5 and y equals 4 or 5, you might get right on this area, and this is the maximum value for z, which is the value of the height of this mountain. So this is level curves, and this is a practical example of how to represent the multivariable in a geometrical way. And as part of the partial derivative subject, this is some of the typical examples to show you on how to understand clearly the meaning of these multivariable calculations. This upper part, this is named as level curve, and this is also named as a surface plot. Okay, so if someone asks you to draw a surface plot, this is the surface, and most surface plots are related to a minimum amount of two variables, in this case x and y, and to represent graphically the function that is going on in this example. But sometimes you don't have the resources, let's say that way, to plot and display a 3D surface plot. So this is surface plot is 3D. It's a 3D plot. How can we represent this same relation or this same function in a two-dimensional space? Well, we need to project the image of this in this representation down here. And if you see this 88, that is this shape over here, is this shape up here. So the same coordinates for x and the same coordinates for y are applicable in this model, but this model is only two-dimensional. So you have here the x equals 4 and the y equals 5 and x equals 6. You may end up with this same value right over here. And this is named as the contour plot. Okay. In Spanish, this is gráfica de contorno 2D. Y esta es gráfica de superficie, ¿sí? Y se llama curvas de nivel porque cada una de estas figuras que vienen aquí es como si nosotros partiéramos esta montaña con una lámina y nos diera una representación de todo el nivel que corresponde a ese valor de altura. Entonces aquí vamos a poner que esto es igual a z, ¿sí? Entonces tenemos la gráfica de superficie en 3 dimensiones y podemos hacer una proyección de la gráfica de superficie en un plano, y ese le llama gráfica de contorno, ¿sí? Y este concepto que tenemos aquí se llama level curves o curvas de nivel. Okay, and now if we move on from this coordinates and usage of the some kind of maps, we can use the same concept to work functions. So you have here, this is x, and this is y, and this is z. Okay, if you are going to plot some function that is z equals a function of x comma y, then you need to have a one value of x and one value of y, and the combination of these two values is going to equal a value of z. Okay, so you have some value for y and some value for x. Let's say maybe here we can say that this is 3, maybe this is 1, and according to the function, this is going to end up with some value of z. Okay, and according to the function that is ruling this relation, then you will have many points from x, y at different heights of this z function, and the sum of all those points is going to form a surface. A surface is like this one, according to the function that you're going to work. But now you are working into input variables. Okay, and this is not limited to a couple of variables. Like in this example, you can have a function and f of x comma y comma z comma q comma r comma s, and this is a 6 variable function. The problem with this type of expression is that it's impossible to represent them geometrically. That's the reason why in all the textbooks, in all your classes, in all the schools, we start to work with the multivariable calculus using only a variable that is depending of 2 variables, because this is the example that we can show you in a geometrical way. So it's the only way that we can plot it and show in this visual manner how it works. Okay, once we are clear with that, let's do an example. Let's say you know the let's talk about the chilling factor. Okay, if you know, you can check the temperature in your cell phone or in your in internet page, and you may have your let's say this is the temperature for today, and the temperature, let's say, is 73 Fahrenheit. But on the top of this value or on the side of this value, you can read something like this: real feel. Okay, and the real feel maybe is going to be something, some value below or above this, maybe 60 Fahrenheit. But why and where this real feel value comes from? Well, there are some factors that affects the chilling of the or the feeling of the temperature. You can have a temperature that is showing 73 Fahrenheit in your instrument, and maybe in reality you are feel that like as 60 Fahrenheit. So this table here is representing that, and let's work this as a couple of variables for input. Let's say that z equal, this is the chilling factor, okay, or real field temperature. And C is equal or is a function of x comma y. And let's say that x is the wind speed. Let me rewrite this. And y, let's say y, that this is the actual temp. Okay. So z is going to be the chilling factor, and the numbers for z are shown here in blue. The wind speed is the top line here. So this is the wind speed is 5, 10, 15, 20, and this is kilometers per hour. And the actual temperature is showing here in this vertical, this column. Okay. So if you want to say, for example, C of 40 comma minus 20. So this is the value for the x variable and the value for the y variables. We have a combination of variables if we want to know what's the value of z at that values of y and x. And let's say that this is 40 for the wind speed and minus 20 for the temperature, and that is equal to minus 34. Okay. So if we want to see or to know what the value for z are for 50, comma 0, and this for a temperature, actual temperature of 0 degrees Celsius, and 50, okay, you can see that the real temperature is near 0 Celsius, but with a wind speed of 50 kilometers per hour, the real fuel for that is equal to minus 8. Okay, so you have the same, this is the same arrangement that we worked in this example. So you have a y-axis and an x-axis, and the coordinates of those two values is going to give you a third value, which is the dependent variable. And this example is very clear to see that we have the effect of the wind plus the effect of the temperature, and this is these two effects combined is going to give you this variable of interest, in this case the chilling factor or the real field temperature. Okay, well, this is a brief introduction to partial derivatives in multivariable calculus. Let's move on to our next topic, which is some examples of 3D graphing. And as always, and um, please let me know your questions or comments so I can take some time and support you. Stay safe.